Imagine, for just a second, that you are handed a check for $114 million.
Oh, wow. That's not a small amount.
Right. And your explicit instructions are to take that money, go out to Stanford, and build a machine that is a staggering 2 miles long.
A 2-mile-long machine, just wild.
Yeah, just a massive, incredibly complex subterranean piece of engineering. And the entire purpose of this giant machine, to prove that almost every single physicist on Earth is completely wrong about the fundamental building blocks of reality.
It really sounds like a wildly expensive, incredibly public gamble. You know, you're essentially betting this massive chunk of federal funding against the entrenched wisdom of the entire scientific establishment.
Exactly. So today we are taking a deep dive into the 1990 Nobel Prize winning MIT SLAC experiments. We're pulling really heavily from the 1990 Nobel Lecture by physicist Henry W. Kendall to explore this phenomenon called deep inelastic scattering.
Right.
And our mission here is to trace one of the most monumental shifts in human knowledge. We are going to explore how humanity figured out that the proton, the particle you probably learned about in grade school, it isn't just a soft, blurry cloud of charge, but actually contains these tiny, unimaginably hard constituents called quarks.
And, to really grasp the magnitude of this, you have to put yourself in the mindset of the scientific community back in 1968. This was not just a routine experiment.
Right. They weren't just checking a box.
No, not at all.
No.
They weren't just tweaking a decimal point on a known constant. This was a complete paradigm-shifting moment. I mean, the data that came out of this accelerator effectively birthed the standard model of particle physics. It completely rewrote our understanding of the universe.
So before we get into the actual machine itself, I feel like we need to understand what the smartest people in the room believed right before they flipped the switch. Like if you asked a top-tier physicist in the mid-1960s what a proton looked like, what would they tell you?
Well, the prevalent belief was that hadrons, which is the umbrella term for particles like protons and neutrons, that they were soft inside.
Soft.
Yes, soft. Earlier experiments, notably by a physicist named Robert Hofstadter, had actually shown that as you increase the energy of particles bouncing off a proton, the scattering cross-section dropped off super sharply.
Okay, meaning the particles they were shooting at the proton, they weren't violently ricocheting off it.
Exactly. They were just passing right through it, or maybe getting gently deflected. The proton didn't act like a hard point. It acted like a diffuse, distributed cloud of charge and magnetic moments. And it was roughly like 10 to the minus 13 centimeters in size. So the assumption was simply that if you hit it harder, you just pass right through more of that soft cloud.
So it's kind of like there's no hard pit in the middle of the peach. You just bite straight through.
That's a perfect way to put it. You bite straight through. And the theories of the day absolutely reflected this soft universe idea. You had frameworks like S-matrix theory and the bootstrap theory, which was sometimes beautifully referred to as nuclear democracy.
See, nuclear democracy sounds like a political thriller to me.
Yeah.
But what did that actually mean for the physics?
It was a super elegant idea, actually. It argued that there were no fundamental particles at all.
None.
None. Every particle was just a composite of other particles held together by their mutual interactions. There was no hierarchy, no absolute foundational building block.
Wow.
And these theories were highly successful at describing the soft, low-energy scattering they were seeing in the lab. So they essentially built this mathematical framework where looking for a hard, point-like subparticle was not just physically wrong, it was considered mathematically unnecessary.
Okay, let's unpack this, because into this perfectly comfortable, highly democratic, soft universe, there's the quark, which, by the way, was a term coined in 1964 by Murray Gell-Mann.
Right.
And he famously grabbed that word from James Joyce's incredibly dense novel, Finnegan's Wake. George Zweig also independently proposed it. But in the 1960s, scientists weren't treating quarks like real objects, right?
Not at all.
They were treating them like a coding trick. Like, hey, if we pretend these little mathematical units called quarks exist on paper, it makes our equations for grouping known particles really elegant. It was a filing system. It wasn't a physical reality.
Right. The theoretical community deeply disliked the idea of quarks as physical, tangible constituents of a proton. The idea was actually considered theoretically disreputable.
Disreputable. I love that word for physics.
Yeah, they had some massive, seemingly insurmountable hurdles to point to whenever someone suggested quarks might actually be real things.
Well, I mean, if I'm claiming that protons are actually made of tiny, physical objects, the most obvious hurdle is that nobody has ever seen one.
Oh, that was absolutely the biggest roadblock. If protons are made of quarks, you should be able to smash a proton and pop a free quark right out. But despite using accelerators, studying cosmic rays, looking literally everywhere in nature, no one had ever found a free quark.
It's like saying, I swear I have a dog, you just can't ever see it or hear it. But couldn't the quark believers just argue that we weren't hitting the protons hard enough to break them apart?
They did. They definitely argued that. But that defense created a second mathematically terrifying hurdle.
Uh-oh.
Yeah. If we couldn't break a proton apart to find a quark, then the binding energy holding those quarks together inside that tiny proton would have to be absurdly high. And to generate that much binding energy, the quarks themselves would have to be incredibly massive.
Okay.
But if they were supermassive, their behavior would contradict all the existing scattering results that physicists had already measured. The math just completely fell apart.
So let me get this straight. They're invisible, and the math required to keep them invisible contradicts reality. Were there other issues?
Oh, yeah. They also seem to violate the Pauli exclusion principle, which is a foundational rule of quantum mechanics. Without getting too deep into the weeds, particles with a certain type of spin 1/2 particles, they cannot occupy the exact same quantum state at the exact same time.
Right, it's kind of like trying to park two cars in the exact same parking spot. You just can't do it.
That is a great way to visualize it. The universe straight up forbids it.
Yeah.
But the way Gell-Mann's theoretical quarks had to be grouped together to form a proton meant they were essentially, parking in the same spot. They were mathematically misbehaving.
Yeah.
And if that wasn't enough, there was the problem of their electrical charge.
Oh, the fractional charges. This
Yeah.
is where physicists really took offense.
Oh, yeah. To make the mathematical model work, these quarks had to have electrical charges that were fractions of an electron's charge, like positive 2/3 or negative 1/3.
Wow.
And the integer character of elementary charges, the idea that charge always comes in whole, discrete packets, was so long established it was practically sacred. Suggesting a particle had a 1/3 charge deeply offended traditional physicists.
So if we look at the landscape at this exact moment, no one can find a quark, their mass makes absolutely no sense, they break fundamental quantum mechanics, and their electrical charges are frankly offensive to the scientific establishment.
Pretty much.
Everyone is perfectly happy believing the proton is just a soft cloud. So whoever wanted to prove them wrong would need an unprecedented, undeniably powerful tool to force the issue.
Which brings us to the Stanford Linear Accelerator Center, or SLAC. It was proposed in 1957, approved by Congress in 1962, and finally turned on in 1967.
And this machine was an absolute beast. I mean, we mentioned the $114 million price tag and the 2-mile lengths.
Huge.
It used advanced klystron technology, which are these massive microwave tubes, to provide the power for a one-pass acceleration of electrons. They were essentially surfing electrons on a 2-mile-long microwave, pushing them to energies up to 21 giga-electron volts.
Right, 21 GeV.
That was the highest electron energies available anywhere in the world at the time.
And the target area where these high-energy electrons finally crashed, that was called End Station A. This was a 200-foot by 125-foot heavily shielded building. And inside they had 3 giant magnetic spectrometers that were used to detect the scattered electrons. These things were huge, literally moving on massive circular rails around the target pivot point. You had a 20 GeV spectrometer for smaller angles, an 8 GeV one for larger angles, and a 1.6 GeV one.
Wait, I have to stop here because this is bothering me. You just said that S-matrix theory and the soft proton theories had already successfully explained the scattering they were seeing. The establishment considered the problem mathematically solved. Why on earth would the government fund a $114 million machine just to shoot electrons at a problem theorists said was already figured out?
Well, if we connect this to the bigger picture, it comes down to the nature of the probe they were using. In previous experiments, scientists were often smashing complex hadrons into other complex hadrons. Smashing a proton into a proton is incredibly messy. It is like smashing 2 Swiss watches together to figure out how the gears work. There are just way too many variables. But SLAC wasn't doing that. They were using electrons.
And electrons are much simpler.
Yeah, electrons are governed by quantum electrodynamics, or QED. They don't feel the strong nuclear force that holds the proton together. They only interact via electromagnetic forces. So this makes the electron an incredibly clean, perfectly understood probe. It's like using a precise laser scalpel instead of a sledgehammer.
Ah, that makes sense.
And crucially, while the theoretical predictions going into the SLAC proposal expected them to just see more of the same soft scattering, the early pre-experiment calculations actually severely underpredicted the actual yields.
Meaning the scientists who built the machine had a hunch that the soft cloud theory wasn't going to hold up at higher energies. They expected a trickle of data based on the old theories, but they got a fire hose.
They really did. But getting that fire hose of raw data was only half the battle. They weren't looking at the whole collision. The SLAC fired in extremely short pulses. The duty cycle, the actual time the beam was on, was so short that if they tried to measure the recoiling proton fragments at the exact same time as the scattered electron, the background noise would have totally swamped the signal.
Because they're smashing things at such high energies, there's just a storm of debris and radiation, right?
Exactly.
So they could only look at the scattered electron and nothing else.
Right. They measured the initial energy of the electron, the final energy after it bounced off the proton, and the angle it bounced at. That's it. But even that electron data was incredibly messy. To actually see a clear physical picture of the proton, the MIT SLAC team had to conquer the unsung hero of particle physics radiative corrections.
Okay, I am really hoping you can help me understand this part, because the text gets really dense here. My understanding is that electrons don't just cleanly hit the target like a billiard ball. Because they are charged particles, when they get violently accelerated or decelerated, they spit out photons. They lose energy as radiation.
Yeah, it's called Bremsstrahlung, which translates to breaking radiation. An electron might start with, say, 20 GeV of energy. But right before the collision, the violent deceleration causes it to burp out a 2 GeV photon, so it actually hits the proton with 18 GeV.
Okay.
But your spectrometer at the end of the line doesn't know that. It just measures the final result and assumes the initial impact was 20 GeV.
Oh. Let me see if I can visualize this. It's like trying to accurately measure the exact impact force of a race car hitting a concrete wall. But the car is randomly throwing heavy sandbags out the window right before the crash, and then again right after the crash.
That is a great start. But take it a step further. You aren't watching the crash happen. You were only allowed to weigh the car after the crash. And somehow you have to use complex math to figure out exactly how many sandbags were thrown out and at what exact microsecond, just to know the true speed at the moment of impact.
That sounds completely agonizing. How do you mathematically correct for sandbags you didn't even see get thrown?
Because an electron could have lost energy via a photon at literally any point in the process. You can't just look at one data point. The team had to use a method involving a kinematic triangle. They had to map out an entire mathematical grid of cross-sections across a wide range of initial energies and final energies.
Wait, what does mapping a triangle have to do with subtracting the radiation?
Well, think of the triangle as mapping a whole grid of car crashes at every single possible speed, from 10 miles an hour up to 200 miles an hour. By studying the patterns of the lower energies where they knew the physics perfectly, they could trace lines up to the higher energies. They could calculate the exact probability of a photon being spat out at every single step.
Oh, wow.
Yeah, and once they had that massive grid of probabilities, they could mathematically subtract the radiative tails from their actual data.
Meaning they had to take thousands of data points they didn't actually care about just to create a mathematical map to clean up the one data point they did care about.
It was a monumental effort. And you have to remember the era, this is the late 1960s. They are doing these massive unfolding procedures on very early computers. The correction was so vital and so complex that they ran completely independent analyses. One team at MIT did the math using one set of approximations, and another team at SLAC did it using completely different mathematical approximations, just to be absolutely sure they weren't fooling themselves.
Honestly, if I'm listening to this right now, I'm probably wondering why they couldn't just build a better detector instead of doing years of agonizing math. But it sounds like the physics of the electron itself demanded this. You literally cannot smash an electron without it radiating.
Exactly. It is an unavoidable law of nature. But the effort paid off. Even though these radiative corrections were the single largest adjustment applied to the raw data, the two independent teams agreed to within a few percent. They reached a 5 to 10% confidence level in the corrections, meaning the underlying cleaned-up data was finally rock solid. The noise was gone.
Okay, here's where it gets really interesting. So the math is cleared away. They look at the raw, unvarnished truth of the proton. And the data was completely shocking to the establishment.
It defied all expectations. Remember how the previous experiments showed that as you hit the proton harder and harder, the cross-section dropped sharply, the proton looks soft?
Right.
But in these new, high-energy, deep inelastic measurements at SLAC, the momentum transfer dependence was weak.
Okay, let's translate weak momentum transfer dependence. Does that mean that as you hit it harder, the electrons didn't just sink into a soft cloud, they get bouncing off at sharp angles?
Yes. It is the difference between throwing a handful of marbles at a fluffy pillow versus throwing those same marbles at a beanbag chair filled with solid steel ball bearings. When you throw them at the pillow, they just thud and sink in. But throw them at the steel bearings and they ricochet off, maintaining a lot of energy.
Wow.
The electrons were ricocheting off tiny, hard points inside the proton.
The steel ball bearings in the beanbag.
Exactly. But what truly sealed the deal, what proved beyond a doubt that these hard points were the quarks everyone had been dismissing, was a mathematical concept called scale invariance, which was predicted by a theorist named James Bjorken.
Bjorken scaling. This is the ultimate smoking gun of the entire deep dive. How does scale invariance prove the quark?
So, in a typical collision with a complex object, the mathematical descriptions of the proton's internal makeup, which are called structure functions, they should depend on two separate variables: the energy you transfer and the momentum you transfer. You need both to describe the size and shape of the object you are hitting. But Bjorken conjectured that at these extreme energies, if the electrons were hitting true point-like particles, those two variables would collapse into a single ratio, a variable they called omega.
I am struggling to visualize why two variables collapsing into one proves they hit a point.
Think about zooming in on a map. If you were looking at a coastline and you zoom in, the shape changes. The jagged edges look different depending on your scale. You need to know how far zoomed in you are to describe what you are seeing. But what happens if you zoom in on a perfect mathematical point?
It just looks like a point. Doesn't matter how close I get, it has no features.
Exactly. If something has no internal size, if it is truly a point, it looks identical no matter how closely you zoom in. It is scale invariant. When the MIT SLA team took their meticulously corrected data and plotted it against this single variable omega, the data points perfectly aligned, they scaled.
So what does this all mean? The math finally aligned with the physical reality. The electrons weren't hitting a cloud. The scale invariance proved they were hitting point-like free constituents inside the proton. The disreputable quark was real. It wasn't just a filing system. It wasn't just a coding trick for theorists. Quarks were physical objects.
The vindication was absolute. This single experimental program fundamentally broke the prevailing S-matrix and soft hadron theories. All those prominent physicists who thought quarks were impossible because of fractional charges and the Pauli exclusion principle, they had to go back to the drawing board. They had to figure out how the universe allowed quarks to exist because the SLAC data irrefutably proved that they did.
And they did eventually figure it out, right? I mean, this discovery opened the door for quantum chromodynamics, or QCD, which is the theory of the strong nuclear force. And when you combine QCD with electroweak theory, you get the standard model of particle physics, the very foundation of how we understand the universe today. All because someone decided to build a 2-mile-long microscope to shoot electrons at a proton.
It's amazing. But you know, this raises a profound legacy question, though. The SLAC data showed that inside the proton, the quarks acted almost as if they were completely free, unbound particles. But if they are free inside the proton, why couldn't previous experiments just knock one out? Why had no one ever found a free quark?
That is the ultimate question. If the electron hit the quark so hard that it ricocheted like a marble off a steel bearing, why didn't the steel bearing fly out of the beanbag?
That mystery was eventually solved by a concept called confinement. The strong force, which holds quarks together, has this bizarre, counterintuitive property where the force between quarks actually increases as you pull them apart.
Wait, really? Most forces get weaker with distance. Gravity gets weaker. Electromagnetism gets weaker.
Yeah, but the strong force acts like a rubber band. If the quarks are incredibly close together, like deep inside the proton, the rubber band is slack. They act like free particles, bouncing around, which is exactly what the SLEC electrons saw. But the moment you try to pull one out, the rubber band stretches. The tension builds. The energy required to stretch that rubber band and pull a quark completely out is so immense that before the band can snap, the stored energy simply creates brand new quark-antiquark pairs out of the vacuum.
Oh, wow.
You reach in to pull out one quark, And you end up with a handful of new particles, but never an isolated quark.
The universe literally uses the energy of your pulling to manufacture new particles just to keep the quarks contained, which leaves us with an absolutely wild thought to mull over.
Definitely.
The MIT SLAC experiments proved, without a shadow of a doubt, that quarks are the hard internal constituents of protons. We know they are there. We have the data. The scientists won the Nobel Prize for it. And yet the text explicitly notes that despite endless cosmic ray searches and massive accelerator experiments, no one has ever successfully found a free, isolated quark in nature.
So I will leave you with this. If we know for an absolute fact that quarks exist, but the fundamental laws of the universe perfectly and eternally hide them away from isolation, what did that tell us about the hidden rules of reality? And what other invisible, perfectly locked away structures might we be completely missing right now, just waiting for someone to build the right 2-mile-long machine to finally see them?